Is it? Okay, cool. Hello all. So welcome to Problem Solving Without Ansibles. This is going to be an introduction to communication complexity, which is a topic in computer science. I'm going to say this again at the end, but I do feel like giving a little disclaimer at the beginning. If you've seen any of Ryan O'Donnell's Theorist Toolkit lectures, which are all on YouTube, the inspiration is a kind word for what I'm doing to his talks. And so I want to be sure to reference him. And also, as like a small homage to Ryan O'Donnell, I decided to make this not in Beamer, but I decided to try making it in Google Docs since I don't have PowerPoint, because he makes all his talks in PowerPoint. And I wanted to see what it was like. So, all right, with that out of the way, let's go ahead and do the thing. So before we start, sort of what are Ansibles in science fiction? This is a photo of an Ansible. And the idea is it's faster than light communication. I think it originally stood for answerable, which then got contracted. And the dream was it would allow colonies to speak in real time. So a lot of times, if you're like a science fiction author, you're like writing some heavy political drama. And in order to make the plot go burr, it's like really helpful if you don't have to wait like 50 years or whatever for communication to go from planet to planet. It's really helpful if you have like near instant communication between places that are light years apart. And we're pretty sure that Ansibles aren't possible, right? So in the real world, featured here, we need to come up with some other way of talking about how this sort of science fiction collaborative problem solving would go. So let's say that we have two people traditionally named Alice and Bob, and Alice is on Earth and Bob is on Mars. And Alice has some string A, some binary string of length n, and Bob has some binary string of length n. And let's say there's some function, f of xy, which takes in binary strings and spits out some binary digit. And Alice and Bob want to collaborate in order to compute f of ab. And the sort of thought process you want to have in mind is that Alice has the entire computational power of Earth at her disposal, and Bob has the entire computational power of Mars at his disposal. And so what's really penalized is the amount of communication back and forth. You can imagine if Earth and Mars were like light years apart, maybe Bob was actually on some planet around Alpha Centauri or something, then sort of the computational complexity of them doing their own little computation is marginal compared to the actual time it takes to send messages. And so computational complexity just counts how many messages you have to send back and forth in order to collaborate on some problem. Yeah, we only penalize communication between Alice and Bob. And I spell Alice stupidly because that's how my good friend spells her name. Blame her. Okay, so a couple quick remarks. We never need more than n+1 many messages, right? Because Alice can just send her entire string to Bob. Bob computes f of ab, and then Bob sends the result back to Alice. And that takes n+1 many messages. So what should efficient mean in this context, since sort of typically we would think of a linear thing as being really efficient, but here a linear thing is like maximally bad. And so the answer is efficient means polylog n many messages. So polynomial in the log of n many messages is what we consider efficient. So for instance, log n to the k for some fixed k, log of log n. And in general, we want the number of messages to be less than some polynomial in log n. And that's what we consider efficient. So as a simple example, let's write d of f, d for deterministic, to be the minimum over all protocols p. So a protocol is sort of the ways that Alice and Bob could possibly agree to share messages, of the max of all the possible inputs of the messages that are sent using p to compute f of ab. So this is for any particular way they could agree to collaborate on the problem, what is the least number of bits that we need in order to solve correctly compute f? And ignore the fact that there's 3 fonts on this slide. That gets fixed in the future. But let's start with a simple example. What is the deterministic complexity of just the equality function? So eq sub n is 1 if x equals y, and is 0 if x does not equal y. Theorem, equality is maximally hard. That is, the deterministic complexity is actually n plus 1, which, like we said earlier, is sort of the worst possible. And there's some really interesting combinatorics that goes into proving this. So let's go ahead and see it. Here's the idea, is we're going to draw a matrix associated to our function f. And our matrix is going to have 2 to the n rows and 2 to the n columns. So you can think about the rows as being indexed by Alice's possible inputs, and the columns as being indexed by Bob's possible inputs. And the AB entry of my matrix is the output f of AB. It seems a little bit silly to think of a 2 to the n by 2 to the n matrix and associate a Boolean function to this, but it turns out to be the really right thing to do, and we'll see why in a moment. So here is an example. Here's the equality function written out as this matrix. So you can see on the left, we have 2 to the n many strings that belong to Alice. And on the bottom, we have 2 to the n many strings, which are Bob's possible strings. And the equality function is just the identity function. We're zeros whenever their inputs are different, and they're ones exactly when the inputs are the same. And there's something in chat. We're going to have space travel. Oh, yikes. OK. So let's see a sample computation with a suboptimal protocol, just to see what the computation looks like, the collaboration, and what we can say about the matrix as we trace through this. So let's say that Alice's string is 0, 1, and Bob's string is 0, 0. OK? Then Alice might send her first bit to Bob, and this restricts the region of the matrix that Bob is interested in, because Alice sends a 0 to Bob. And so now Bob knows that he's only really interested in rows where the first bit is a 0, right? And then maybe Bob sends his second bit to Alice. And so Bob's second bit is a 0. And so now Alice and Bob are only interested in the places where Alice's first bit is a 0 and Bob's second bit is a 0. So this again restricts the region of interest. Then maybe Alice sends her second bit to Bob, and this restricts the region again to now only these guys, where we know Alice's string exactly, and we know Bob's second bit is a 0. And now we're done, and we can halt the computation. Alice and Bob both know what the answer should be, because the region that we've restricted to is monochromatic. There's only zeros in the region, and so we now know what the output has to be. The output has to be 0, and we can stop. So why are we interested in this? Well, in general, when we follow any protocol, and remember, if we want to prove this is really a lower bound problem, right? We know that we can do it in n plus 1. The claim is that we need at least n plus 1 as well. So in order to show a lower bound, we have to argue against all possible protocols. And this is going to give us some combinatorial way of doing so, as is often the case in computer science. So in general, when we follow some protocol, each message is going to restrict the region of interest in this matrix. And moreover, each region we restrict to is a combinatorial rectangle. And by a combinatorial rectangle, we mean a region of the form A0 times B0, for some A0 is a subset of A and B0 is a subset of B. So we're only interested in things that look like the product of two subsets. So it can't be any old region. And so any protocol correctly computing F must partition our matrix into combinatorial rectangles, each of which is monochromatic. And I think I say in fancy lingo, this is called monochromaticity. And so this is good, because now if we can argue that no partition exists, right? If we can argue that you need a certain number of rectangles to solve your problem, then we're done. We have a lower bound. So let's see this in action for the equality function. Here's our matrix. Notice the top left entry must be a 1-by-1 rectangle, right? Because if it were not a 1-by-1 rectangle, let's say maybe it included more entries from this row, well, then it would have to include a 0. And similarly, if it included more entries from this column, it would have to include a 0. So this guy has to be a 1-by-1 rectangle. And similarly, every diagonal must be a 1-by-1 rectangle. But we know there's 2 to the n rows and 2 to the n columns, where of course here n is 2. And so we actually have 2 to the n rectangles, and we haven't even touched the zeros yet. So we have more than 2 to the n many rectangles necessary. But each message we send partitions our old rectangles in half, right? If I'm interested in some rectangle and then I get a 0 from Alice maybe, then that tells me to partition my rectangle into two smaller rectangles, a rectangle where Alice sent a 0 and a rectangle where Alice sent a 1. And so at most, we divide our number of rectangles in half, or sorry, we double the number of rectangles, to say that in a slightly more coherent way. And so the equality requires at least log 2 of 2 to the n many messages, because you can only double your number of rectangles on each stage. And so you need to have log many stages in order to get it. And so we have more than n many messages. So the least that can be is n plus 1 many messages. And we already have a protocol that does it at n plus 1. So n plus 1 is actually best possible. OK, so before we move on, because now we're going to switch from deterministic, D for deterministic, to a randomized protocol. Do people have questions about any of this?
Yeah, can you go over the situation again? Like they're on different planets. Why can't Alice just put in both entries into the computer on Earth?
Because Alice knows her string and Bob knows his string. And so Alice knows A and Bob knows B, and they want to collaborate to compute f of AB. So
Okay.
Yeah, so Alice has some string over here and Bob has his string over here, and they want to compute some function of both strings, but Alice doesn't know Bob's and Bob doesn't know Alice's.
Okay.
And so you want to know how many messages you send back and forth in order to compute it. Yeah, and so you can imagine if communication is the really expensive thing in this setup, like sure, Alice could send her entire string to Bob, Bob could send his entire string back, right? Or something like that. But we want to know if there's some better way of solving this problem. I don't know if there's any good motivation for solving this problem. Once I heard about it, I just kind of took it at face value and thought it was interesting. I'm sure there is some reason that like a software engineer might care about this problem. I would be curious to know about it. But I don't have any better motivation than this, unfortunately.
So can I ask, do they both need to compute f of AB, or
yes,
is that how this is
so
going?
they both need to know f of AB by the end, but that at most adds one extra bit of communication, right? Because
Right.
if Bob knows the answer, then Bob just sends the answer to Alice.
Got it.
Yeah, that's why equality takes n plus 1 many bits, because Alice sends her entire string to Bob, and that takes n many messages, and then Bob sends the answer back, and that takes 1 message. Okay, so we saw that equality was somehow maximally hard, right? So when you see something that's hard, at least in computer science, one question you might have afterwards is, okay, can I make this easier by using some amount of randomness, right? This tends to make things easier. So what if we only want the correct answer with high probability? Okay, so there's a lot on this slide, but theorem. Alice and Bob can communicate only log of n many bits. So this is now efficient in the sense outlined above, so that if A equals B, then they always correctly say, yes, we're equal. And if A is not equal to B, then we only incorrectly say, yes, we're equal, with probability less than 1 over n. And we say that such an algorithm has one-sided error. So we got this to be efficient, and sort of we never get a false negative. And with some low probability, with probability less than 1 over n, we might get a false positive. Okay, and we say this has one-sided error. So let's see this in action. This is a really fun algorithm. So let's say Alice has some binary string and Bob has some other binary string. Wait, are there strings the reverse of each other? That's hilarious. I did not plan that. No, not quite. Not quite. Okay. Anyways, so what Alice and Bob do is they associate polynomials to their strings, where they say, so Alice's string is 1010, So she reads those off as the coefficients of x, x squared, x cubed, and x to the fourth. And similarly, Bob's string starts 0, 0, 1, 0. So 0, 0, 1, 0 are the coefficients on x, x squared, x cubed, x to the fourth. Okay. And now Alice is going to think of a prime between n squared and 2n squared. So she's going to come up with some prime q between n squared and 2n squared, which I guess is guaranteed by like Bertrand's postulate or something. And she's going to send q to Bob. Okay. And this, we're within budget. We want to do this in log n many bits. Well, it takes log q many bits to send q to Bob, because log q is like the number of digits required to write down q. But q is, remember, at most 2n squared. So this is at most log of 2n squared, which is just log of n. So we're within budget. And now Alice is also going to think of some alpha in fq. So she's going to pick some element of the finite field of order q, and she's going to send that to Bob as well. And this is going to, again, it's going to cost log of alpha many bits to do this, but that's okay, because alpha is less than n squared. Well, alpha is less than q. So that's also log n many bits. And now, and she chose alpha randomly, I should say. It's okay if you choose q deterministically, but alpha should be random for what follows. And then she's going to evaluate alpha on her polynomial and send that to Bob. And again, that's going to take O of log n many bits, because when I apply a polynomial to some field element, I get some other field element, and we know it costs log n many bits to send a field element to Bob. Then Bob over here is going to think, is Alice's answer equal to my answer? So Bob has access to q, to alpha, and to Alice's answer. So he does the exact same computation over here. He evaluates he evaluates his polynomial at alpha, and he says, are these equal? And then he's going to send back yes or no. And we're going to just say that Alice's and Bob have the same string if PA of alpha equals PB of alpha. Okay, so first of all, are we within budget? Yes, because we sent log n many bits to send q, log n many bits to send alpha, log n many bits to send P of alpha, and then Bob has to send 1 bit back in order to make sure they both know the answer at the end of the day. And this is like 3 log n, which is of course O of log n. And why does this work? Well, if A equals B, then the polynomials are equal. And so no matter what alpha you choose, you're guaranteed to have, when I evaluate them, you get the same answer. So 100% of the time, if the strings are equal, Bob tells Alice, yes, they're equal. What about the other way? Well, if A is not B, then the polynomials aren't equal. And so asking when they're equal on this input is asking when PA minus PB, which is some other polynomial, evaluates to 0 on alpha. But we know that PA minus PB is some polynomial of degree n, right? If you remember how we constructed PA and PB, they're polynomials of degree n, and the difference of two polynomials of degree n is at most a polynomial of degree n. And so PA minus PB has at most n many roots. And so the probability of a false yes is the probability that alpha is sort of accidentally a root of PA minus PB, but that's at most the degree of this polynomial divided by the number of guys in our field that we could evaluate them on. But we cleverly chose q to be bigger than n squared. And so this is at most n over n squared. And so we have at most 1 over n probability of accidentally saying yes. Cool. So before we move on, do people have questions about this protocol, questions about any of this?
So obviously, if you're communicating on a planetary scale, you would want to send like big pieces of information at a time so that it's more likely that it's correct. As n grows larger. That's
true. I guess you would. Yeah, the sci-fi device is really some clever framing principle to try to get people to the talk, unfortunately. Really you want to think about counting the number of bits we send. And so Alice and Bob are supposed to agree in advance that Alice is going to send like a bunch of bits to Bob. And that bunch of bits is going to represent Q. And then maybe Alice terminates with like some way so that Bob knows that that she's done sending Q, right? Yeah, and so yeah, we're counting the number of bits that are sent. But I agree, yeah. For a real like interplanetary society, it probably makes sense to amortize this cost, sending as much information in one trip as possible. Okay, so maybe sci-fi wasn't the best framing after all. But yeah, other questions about this? And then if not, we can go ahead and move on.
Well, I guess my real question was 1 over n is that good? Like we're happy with that?
Oh, yeah. Oh, I understand. Yeah, you want to imagine A and B are really long strings. And
Yeah,
so,
okay.
1 over n is really good. 1 over n error, if your strings are of length 100, then like imagine like we finally send Elon Musk to Mars, good riddance, and he and Grimes are like trying to decide if they have the same bank account balance, right? Then n is some absurd number of digits, and probably 1 over n error, you're fine. Okay, so can we do better? Is always the question to ask. We know we can do it in log n, and we've decided log n is efficient, but maybe we can do better, right? You know, it's like that move in chess. If you see a good move in chess, you should look for a better one. We know we can solve this problem efficiently. Can we solve it more efficiently? And the answer is yes, if we cheat. So how do we define cheating in this instance? Well, let's go back to our setup. We have Alice and Bob over here on different planets. Alice has some string, Bob has some string, and there's a bunch of random bits written in the sky that Alice and Bob can both see. So in the previous example, Alice had to choose alpha randomly, but of course Alice was like, Bob didn't need to know any of the randomness, right? Alice could like flip a coin on her own terms and come up with a thing and then send it to Bob. Whereas now we're asking sort of, there's randomness, but everyone can see the randomness, right? And so you can imagine this makes our life easier, because if everyone can see the randomness, then the randomness can do some of the communication for us, right? Because Alice and Bob both have access to this randomness. Cool. So just saying random bits in the sky is a little bit aphysical. So you can instead imagine there's some star, right? And Alpha and Bob both agree to look at like the temperature of this star that they measure really precisely. And like the decimals of the temperature of this star probably form a pretty good pseudo-random sequence of numbers for them to use. But for us, we're not going to worry about like stars and things. We're going to just talk about random bits written in the sky. And Theorem, in the public randomness model, which is what this is called, Alice and Bob can solve equation n, or equality on n, with probability of false positive less than 25% using, and now it's audience participation time, how many bits do you think they can do it in? I'll give people a chance to say things in chat or to otherwise indicate their answer, but how efficiently do you think we can do this? The answer may surprise you.
6.
6 constantly. So you think constant in the length of the string, you can do it.
Mm-hmm. That was secretly an American Dad reference.
Oh, I'm sorry.
Is it gonna be like tons of logs?
Tons of logs is a good guess. Actually, your first guess was closer. You can do it with 3. So actually, this is like incredibly surprising to me, right? That constant in the length of your string, you can always do this, which is like bananas, right? Even if you want to check equality for like, I don't know, 10,000 linked strings, with only 3 messages, you can know with decently high probability that they're the same. And of course, nothing is special about 25% in this setup. So a slightly more general theorem, and the one that you would imagine shows up in the paper, is if you want a probability of false positive, if you want a probability of false positive at most epsilon, then you can do that with O of log of 1 over epsilon bits of communication. But this is uniform in n. So imagine epsilon is like 1/1000th, right? Then this is O of 1, which is incredible. So let's talk about how this works. Once you see it, it becomes obvious, as with so many things in life. But so take a moment to just like appreciate how surprising this theorem is before it loses its wonder. Okay, so here's the idea. There's random bits written in the sky. And we're going to imagine those random bits. We're going to look at the first n many random bits, and then we're going to look at the second n many random bits, and then we don't need any more randomness, but it's there. And Alice is going to send the dot product of her string and R, where of course this dot product is taken mod 2. So R is of course the sequence of the first R bits. And then she's going to send the dot product of A of her string and S. And then Bob is going to say, do your dot products agree with my dot products? And he's going to send back yes or no. So this is 3 bits of communication. Why does this work? Right? And the answer is if A equals B, okay, then clearly A dot R equals B dot R always. Otherwise, since we're dotting with some random string, you can convince yourself, I didn't write it on the slide, but it's not hard to see that taking the dot product with some random string is 1 with probability 1/2 and is 0 with probability 1/2. So if you ask if A and B dotted with R are the same thing, then that happens with probability 1/2, right? Because first you fix what you want your answer to be, and then Bob checks whether his answer is that. And there's a 1/2 probability that that succeeds. So the probability that both checks succeed is actually 1 in 4, which is exactly what we were looking for. But as we said, 25% isn't special, right? If you want the probability of a false positive to be less than 0.01, say, then sending 7 bits is always enough. And that's because, well, 1 over 2 to the 7 is the probability that all your checks pass. And that's like 1 over 128, which is less than 100. So that's how that works. Yes, this dot product is happening in Z mod 2. Exactly. So another way to say this, the dot product is, I think, a nice way to picture what's happening. But there's another way to picture what's happening. Maybe I should have put a slide on this because I anticipated maybe talking about it, but I was lazy and I didn't write up a slide on it. Another way to picture this is if you're familiar with these things called error correcting codes, then what an error correcting code does is it makes it so that you can transmit some slightly redundant. If Alice is sending a message to Bob, and this is now a completely different setup. The idea now is Alice is sending a message to Bob along some noisy channel, right? So maybe like it's the internet or something, and you pick up some random bit flips along the way. Then Alice sends her string to Bob, and we want to know that Bob can not only detect that some bits got flipped along the way, but ideally, Bob should be able to correct for the bit flips. And rather than just asking Alice, hey, could you send that message again? Bob can sort of be like an independent person and fix the problem himself. And we want to do that ideally with relatively low redundancy. So I mean, I guess you could just send your message 3 times, right? And then Bob could, for each bit, could just take the majority. But that's not great. So you want to know that you don't send too many extra bits. You don't make your message too long. And yet you also want to know that Bob can correct lots of errors. And there's some tension because you can correct more errors if you send more information or send more redundant information. And there's lots of really, really cool ways to send error correcting codes. If you want to talk about them, feel free to ask me questions either after the talk or like in life. I get kind of geeky about error correcting codes. But one error correcting code, which is optimal in a certain sense, is called the Hamming code. And the Hamming code is really, really bad in terms of message blowup. So for the Hamming code, you actually end up sending like 2 to the n many bits for an original message of length n. But it's like really, really good in terms of rate, or not in terms of rate, in terms of minimum distance. So it's really, really good in the sense that, yeah, you're sending lots of bits, but if half of your bits get flipped, you can still recover, you can still reverse engineer what the correct string should have been. So on the one hand, your rate is kind of crummy. You have to send like tons of redundant information. But on the other hand, you can fix like an optimum number of bits, right? You can imagine if more than half of your message is corrupted, there's no way of possibly recovering the original message. And so another way of imagining this protocol is Alice and Bob just agree to use the Hamming code in advance. And rather than Alice sending, and so again, the Hamming code sort of makes it so that if your string, it sort of amplifies any discrepancies in their strings, where what an error correcting code does, one way to think about it, is if Alice's and Bob's strings disagree on some small number of digits, then when I encode them, they now have to disagree on some large number of digits, because it has to be a large enough number of digits that I could correctly figure out which one of Alice's and Bob's strings I started with if some of the digits get flipped. So there have to be like lots of differences between Alice's and Bob's string after encoding them. I really should have put up a slide on this. I feel like I'm just rambling at this point, but it's interesting, so I'll keep going. And so since we've amplified the number of errors that Alice's and Bob's strings have, then the Hamming code, like we said, is optimal. It makes it so that if you started with two different strings, actually half of the digits, half of the digits in the new string are different. And so now you think of the random bits in the sky as being indexes into the new string. So the new string has length 2 to the n. So picking some random sequence of length n tells me which bit of my new really long message to look at. And so by sending some random bits of my really long string, and you can see this is the sense in which the string is doing some communication for us, right? The random bits written in the sky are sort of telling Alice and Bob, okay, where in my code should I look? And Alice sends what her code word thinks is at that position and where her code word thinks that position is. And same thing, because Hamming codes have minimum distance 1/2, we see there's a 1/2 chance for in each check, there's a 1/2 chance that they sort of accidentally have the same thing. And that really is exactly what's happening here, because the way that the Hamming code works is the 2 to the nth, or the ith entry, the ith bit in my encoded message is literally just my original string dotted with I written in binary. So that's why you get such terrible blow up, because you're literally dotting against all 2 to the n possible strings. Okay, that was more of a ramble than I intended to go on. But if you like linear codes, that's another way of viewing this. At this point, I've even forgotten what the original question was, regrettably. So if you could either say it again or say if anything in that ramble helped, that would be great. That was a slightly longer tangent than I intended. Okay, well, outside of me getting excited about linear codes, yeah, so 7 bits is always enough, right? And in general, in order to get the probability of some error less than epsilon, we need to know that 2 to the negative number of messages is less than epsilon. And that's a really easy equation to solve. That happens exactly when you send more than log of 1 over epsilon many messages. And so log of 1 over epsilon plus 1 is enough. Okay, but how much are we cheating by, really, right? We've said that, like, right, we know we're cheating because the random bits in the sky are giving us some bonus information. What if we really wanted to insist that there are no random bits in the sky? How can we make that happen? Well, this is now Newman's theorem. And Newman's theorem says we're not cheating by that much. And so before we wrote D of f for the deterministic communication complexity, now we're going to write R sub epsilon pub of f for the randomized public communication complexity. So this is with random bits written in the sky. And we also write R sub epsilon priv for the randomized private communication complexity. And of course, epsilon is the amount of error that we're willing to tolerate. And okay, so there's this theorem due to Newman, which says that if you're willing to account for a little bit of extra randomness, or not randomness, if you're willing to tolerate a little bit of extra error, then you can actually convert a private coin model, you can convert a public coin model into a private coin model at the cost of a little bit of extra uncertainty, so delta more uncertainty, and at the cost of log n many bits. So let's say that one more time. So if this is how many messages you have to send in a public setting, then you never need to send more than that plus log n many bonus bits if you set delta to be like 0.01 or something. Obviously, the number of bonus bits you have to send also depends on how little complexity, how little bonus error you're willing to take on. Yeah, exactly. So this says at the cost of a little bit more error and log n many extra messages, we can turn a public randomness protocol into a private randomness protocol. And this agrees with our result from earlier. If you remember the protocol where we encoded Alice's string as a polynomial, only Alice needed the randomness, and we needed log n many messages. And in the public coin protocol we discussed, we got it down to O of 1 many messages. So we have a discrepancy of O of log n. And Newman's theorem says you'll never do worse than this. You will never need more than a log n discrepancy between these two things. And so how does the proof of Newman's theorem go? We don't have time to get into it right now, but the idea is you turn the random bits written in the sky really, as a form of communication, are sort of the only obstruction. And so you can imagine, if you can show that you don't use too many random bits, then Alice can just flip her own coin to get random bits. And then Alice can send her random bits to Bob. And then they proceed as though it were a public coin protocol. And so you can imagine if you don't use too many bits of randomness, then Alice sending her random string to Bob is just an extra log n many messages, because log n is the amount of time it takes to encode some number. And we don't need to go into that too much. If you want, you can find this basically anywhere. Any textbook that talks about communication complexity will prove Newman's theorem. It's in lots of papers and handouts on the internet. But it's really interesting, and it sort of morally shows us that using public keys is okay. We never pick up more than a log n factor. And public keys are really convenient in ways that we saw earlier. So public keys have become sort of the de facto standard of communication complexity. And Newman's theorem justifies that philosophically. Even if you don't believe in public keys, well, if you really want private keys, you can. You just have to pick up an extra O of log n many messages. Like I said, for more information, you can see Ryan O'Donnell's CS Theory Toolkit, which is a fantastic playlist on YouTube. He's a phenomenal presenter. If you enjoyed any of what I said, you should really go spend some time with the real Ryan O'Donnell instead of a bad knockoff. And like I said, I'll link that playlist when I post this recording to my blog. I'll link that playlist on the blog post to make it a little bit easier to find. And that's all I've got for you. So thank you so much. If you have questions about things, I will happily talk about them. Great.
Nice talk.
Thank you.
I see some muted applause.
I'll go ahead and stop the screen share and stop the recording. There should be a button for that.